Okay? These pages are the same size, whether it's virtual memory or physical memory. The idea is that we have to provide a mechanism that will translate this virtual address into a physical address so we can actually get the data out of main memory. Right? So the first part of that is easy. The virtual page offset is the exact same as the physical page offset. Second part is a little harder. We use the page table base register, which is set for every process when it starts, and it points to the start of the page table for that process. So then we use that as the base, and then we use the virtual page number to index into that page, into the page table, to look at the page table entry. This address that is presented here is the page table entry address, the address of the page table entry for that particular virtual address. Okay? If the valid bit is not set to 1, meaning it's a 0, that means that we do not have that page loaded into physical memory. In which case, we take a page fault, and the page fault handler runs, and then depending on whether you have legal access to that page or not, it either gives you a seg fault or a protection fault, or it loads the page into memory and restarts the program, and this whole process starts over, at which point we expect that this bit is set to 1 and it is valid, and we read out the physical page number part of the address, and now we have a complete address to present to the memory system. Okay, so this is from 60,000 feet how this works. This is generally controlled by the memory management unit. So the CPU issues an address, and every address it issues is a virtual address. I will repeat that several times today. Okay? The memory management unit then will use the method of combining the page table base register and the virtual page number to present the page table entry address to the memory system. And then the memory system will return the page table entry for that particular virtual page number. The memory management unit will use that entry to construct the physical address, and then the data will be returned. That's what happens when we get a page hit. Okay? Now, you might ask yourself, is there anything special about page table entries versus other data that's held in the program in terms of where it's stored and how it's addressed? In other words, is a page table entry addressed with a virtual address or a physical address? Anyone want to answer that question? Virtual address. Every address presented by the CPU is a virtual address. Okay? We'll get to how it's different, but generally it is the same. So page table entries are just like any other data in memory. They sit in main memory. They are cached in the cache. Okay? So actually what happens when the page table entry address is presented to the memory system, it's first presented to the cache as any other kind of data request. If it's a hit in the cache, meaning the page table entry is in the cache, then the page table entry is returned directly from the cache, and we don't go to the memory system. If we get a miss on that page table entry address, then we have to go to memory, bring it back to the cache, in which case it's returned to the memory management unit. This cycle of hitting or missing is exactly the same as for the physical address for the data. Okay, how likely is it that you are going to get a cache miss for a page table entry versus a regular, the entry of that's constructed out of the physical address? What's your guess on that? Somebody? Yes?
Probably much less likely to get a miss from the table entry.
Why?
Because locality, you'll be likely be at like going to multiple things in the same table.
Right, so the idea here is that every single address of data that we try to read or write must go through this two-step process of generating a page table entry address and getting back the page table. So the likelihood that you've kicked out the page table entry is very low. Okay? If you do that, of course, it's very expensive, because even if the data happens to be cached, the page table won't be, and you'll take a cache miss. Okay? So let me reiterate one more time. Page table entries are just the same as any other data. Okay? Now, this begs the question of, my God, isn't this slow? Every single piece of data I want to access, I have to make 2 memory accesses for. Anyway, that's what it looks like so far. Okay, so obviously, you know, computer architects are smarter than this, so real memory management units don't do that, and they have the translation look-aside buffer, or the TLB, which I talked about on Tuesday. Okay, so the idea here is that in addition to caching normal data in the L1 cache, page table entries are treated specially by the memory management unit, and they are also cached in the TLB. Okay? So the way an actual translation looks like is the virtual address is presented from the CPU to the memory management unit, and then the memory management unit uses the virtual page number part of that address and looks in the TLB, which is generally a highly associative cache. Okay? And to see whether or not the page table entry for that virtual page number is in the TLB. If it is, if we get a TLB hit, then the page table entry is returned to the memory management unit, and we can directly construct the physical address. We don't have to go to main memory for the page table entry because it's cached in the special location. Okay? And then we get the data back. If we get a TLB miss, then it's like what was over here before. And we have to go to the cache. Okay? The hope is that a very few small number of entries in the TLB will provide us with lots and lots of hits so that we don't have to make 2 memory accesses for every memory request by the CPU. And this is generally true because of locality. Okay? And you can monitor this on your system. When your system slows to a crawl, you can look at the page fault rate and the TLB fault rate. And when they say page fault, it's the same thing as a miss in the page tables. Or a TLB fault is the same thing as a miss in the TLBs. Okay? Okay. Oh, I guess I had this anyway. If I have a TLB miss, I present the page table entry address to the system. I get back the page table entry, and it puts it in the TLB and gives it to the memory management unit. So the next time I access that page, if I do it soon enough, I'm going to have that entry in my TLB, and because of locality, that generally works. Okay? Any questions so far? Yes?
So we talked about how if you, before we talked about the TLB, when you had a page fault, then you would go to memory,
Yeah.
cache the data, and then try again.
Okay, there's a difference between a page fault and missing in the cache.
Okay.
If it doesn't mean that I have a page fault if I have a cache miss.
Okay.
If I have a cache miss here, I go and get it and I get the page table entry back, and if it turns out that page table entry says it's valid, that is not a page fault.
Right.
It was a cache miss in the process of translating the address.
Yeah, never mind that.
Okay? But that's a good distinction to make. Okay, so what I haven't talked about is how these page table entries are stored in main memory. And if you think a little bit about a 64-bit address space, these page table entries can get sort of large, right? So let's say we have a 4K page like we do on the i7, okay? So in a 64-bit address space, we're going to have 8-byte page table entries. That would mean we would need 32,000 terabytes of page table. That's a lot of page table. Okay, so I don't know how many computers we'd have to get together at CMU to get 32,000 terabytes, but we probably don't have enough of that. Okay, so there's got to be a cleverer way to do this, and there is. It's a hierarchical page table. Okay, so the idea here is we're going to break up the virtual page number so one part of it access, in this case this is a 2-level page table. The first part is going to access the level 1 page table, and it will have a pointer, not a page table entry, but a pointer to another set of page table entries. In this case, these are going to be page table entries. And then we'll use the second part of the address, the VPN, to actually get this out. Okay? So This is generally the way modern servers and laptops and probably your iPhone work. They have multiple level page tables that allow us to save a lot of room. So for instance, if we have, here we have, let's say, a 32-bit address space, okay, and we're going to have 4K pages, so that means 12 bits. The bottom 12 bits of my address is the page offset, because my pages are 4K each. Okay? And I need, let's say, 4 bytes to represent my page table entry. That's enough to hold everything. So that means if I store a chunk of my page table in one page, because I have 4K pages and 4-byte page table entries, I get 1,000 page table entries per page. Okay? So remember that the page table is just like normal data. I'm going to store it in pages that get swapped in or out as needed by the virtual memory system. So I have 20 bits left for the virtual page number, right? 12 bits for the page offset, 20 bits for the virtual page number. I'm going to break that 20-bit field into 2 10-bit fields. The first 10 bits will allow me to access the level 1 page table, letting me access one of 1,000 of these pointers. These are not page table entries. Okay? These are pointers to page table entries, each one being stored in one complete page. So if I think about virtual page number 0, the first 10 bits are 0, so that gets me to this pointer, and then the next 10 bits are 0, which gives me this particular page table entry, which corresponds to virtual page 0 here. I don't know where it's going to point in real memory. Okay? Now, if you're not using a big chunk of virtual memory for your process, then you can have a null stored in this first level page table, and it doesn't have any of the page, it doesn't have the second level page table for that particular first 10 bits loaded in physical memory. So you can save a lot of space. Okay, so whenever there's a big gap, and there generally is, particularly on a 64-bit address space, you're going to be able to save all of those page table entries that you didn't need to load because of the hierarchical nature of this page table. Okay? Now, if we have K levels, that was 2 levels, what we're going to end up doing is breaking up the virtual page number into K separate fields. The first field will get me the level 1 page table, which will then point me to the base of the level 2 page table, and then I'll use the second piece of this virtual page number to index into that, and I'll keep doing that until I get to the very last level, in this case level K, and then the level K minus 1 pointer plus the bits I have in this piece of the field will give me a pointer to the page table entry which has the actual physical page number. So in a level K virtual memory system, if I make an access, the CPU issue says I want to access a particular virtual address, and that virtual page number is not cached in the TLB, how many memory references am I actually going to make in order to satisfy the one virtual reference that the CPU made? This is a K-level page table. The virtual page number is not cached in the TLB. How many actual memory references get made? I have K plus 2. Do I have any other guesses?
K plus 1.
K plus 1. Any other guesses? Okay, so it's going to be K plus 1 because we're going to access each of the level K tables. That's K memory accesses, and then with the physical address I will access the data. So it's K plus 1. Okay? So you can see that as you get to have bigger address spaces, which forces you to have multi-level page tables, you're going to end up really relying on the TLB to a certain extent. Otherwise, each access can turn into lots of accesses. Okay. So that was all sort of review, not that little last part, I guess. So we talked about fork very briefly at the end of the lecture on Tuesday, but we've also talked about it before, and you're hopefully very comfortable with it in Teach Lab. Okay. So the way fork works, if you'll recall, is that the parent process memory image is copied to the child process. They both start off with the exact same memory image. And then as the child and the parent start running, they start modifying their data, and it's their own private data. Okay, so if I have a program that's 100, let's say currently has 100 megabytes or a gigabyte worth of data, and I fork off a child process, the naive way to think about that makes that a really expensive operation, right? Because you would actually have to copy a gigabyte's worth of data to get it ready for the child process. Okay? That's hugely expensive. It's particularly expensive if I'm going to do an exec right afterwards, which wipes all of that data out, right? But virtual memory comes up to the rescue, so we don't actually fork by copying. Instead, what we do is we only copy the page table. So here's how it works. Let's think first about a situation where I have two processes. I'm not going to talk about how they were started right now. And they want to share some object. There's some shared object. And it's located at this particular address in process 1, and it's mapped into physical memory over here. Okay, remember that the process has no clue about physical memory, but its address is just right over here. Okay? And then process 2 wants to share this. So what it does is it sets up its page tables so that it maps its area of virtual memory that it thinks the object lives in to the same area of physical memory. Okay, notice that they can be different. That's the beauty of virtual memory. Okay? So this is how things are shared. So if process 1 writes into it, then process 2 can see it, and vice versa. Okay? For forking, we don't want that. We want our own private exclusive copy of the memory right at the time of the fork. So there's this concept of copy on write. Okay? So we have process 1. Let's say they have some piece of memory that they want to treat as private to themselves. Okay? But when it gets started, some other process also has a copy of it. It wants to have a private data, but at the time when they both get started, it starts out as the same data, just like in fork. So what we can do is we can set up the page tables for both of these processes to point to the same physical memory. But then mark that page table entry as read-only for the process. Okay, so as long as these processes are just reading from this data, nothing happens. They can both go ahead and read from it. But as soon as one of the processes wants to write any single byte in this private copy on data, copy on write area, then what we'll do is we'll take a page fault. But the page fault handler knows that this is actually data that this process is allowed to write to. So what it does is it makes a copy. So here we just wrote to a piece of this. It copies the portion of memory that corresponds to the page that I just wrote to some new place in physical memory. And then it sets the page table entry for this to be read-write. Okay? So here I had a big chunk of memory, let's say, and I decided to write to one piece of it. I incur the cost for copying that memory. And now I can read and write to it as much as I want to, but I don't incur the cost of copying the rest of this memory. Okay, so in some sense, I get to copy huge chunks of memory almost for free. And then lazily or on demand, I actually do the mem copy that I need to if I actually want to write to it. Okay, so it's a very cheap way to get multiple copies of data to different processes. Okay? This is exactly what happens on fork. So right at the time that fork is called in the parent process, what does the kernel do? Well, it creates an exact copy of the parent page tables for the child, sets up some other structures, and then in both the parent and the child, it marks all those page table entries as read-only. So it could be I have 100 megabytes or a gigabyte but I only had to copy a few sets of pages. Okay? So I really saved on how much I had to copy. In fact, if you think about the hierarchical nature of a multi-level page table, I might only have to set 1 or 2 page table entries to read-only, because all of their children will then be automatically marked as read-only. Okay? So then we flagged both of these areas as read-only and copy on write. And now when I return from fork, the parent and the child both have identical copies in virtual memory. It's sort of a weird concept. There's only one physical memory of this. And as soon as the parent or the child writes to any of this memory, we will on-demand copy it. Okay? So fork turns out to be not that expensive, even though if you think about what it has to happen naively, it sounds like a very expensive operation to copy the whole thing. And this is particularly beautiful if fork is followed by exec, like in your Tisch when you're starting up new programs, because what you do for the child is just create the identical page tables, and then as soon as exec comes and we throw all that memory away, we didn't do any unnecessary copying of physical memory. Okay? It all works together. It's sort of nice. Okay. So now we've got pretty much understand all the basic concepts, I hope. And so I'm going to go through sort of a nitty-gritty example of what happens sort of piece by piece. Okay? So I hope you'll bear with me. Let's see if I have the right display here. Nope. Yeah, I guess I can use that one. So how do I get the screen to go up? So I should turn the lights on too. Okay. So remember the basic symbol, the basic terminology I'm going to use here. N is the size of the virtual address space. M is the size of the physical address space. P is the size of each page. Capital P. Small p is the number of bits we need to access something in that page. Okay, a virtual address has 2 basic components, the page offset and the page number. And the page number itself is divided into 2 pieces, the TLB index and the TLB tag. So we can think of the TLB as a cache, and it's a set associative cache. If it was a fully set associative cache, then the index would be 0. If it was a fully direct map cache, then it would be as big as the number of sets that I had. Well, for generality, we'll have both of these pieces in this example. And the physical address also has a page offset, the same as the virtual page offset, and a page number. And then the address itself can also be divided into a cache offset, into the cache line, depending on the block size of the cache line, the cache index, and the cache tag, because it's a set associative cache as well. Okay? So imagine we are on a system that has 14-bit virtual address space and a 12-bit physical address space. Okay? And we're going to say that the page size is 64 bytes. So how big does the offset have to be? 6 bytes. 2 to the 6 is 64. Okay? And that's going to be the same in both the virtual address and the physical address. Okay? Now, we're going to have a very simple single-level page table where it's accessed by the virtual page number. And if it's valid, then we'll have the physical page number in it. And if it's not valid, then we'll just have nothing in it. It doesn't matter. Okay, so I'm showing only the first 16 entries of the page table. Given that we have 14 minus 6, or 8 bits for the virtual page number, our page table should have 256 entries in it, 2 to the 8. Right? Okay? So the TLB, we're going to assume, is 16 entries with 4-way associative. So that means that the virtual page number can be broken into 2 pieces. the TLB index, which is 2 bits, which will tell me which set I'm going to look at. And since each set has 4 lines, I'm going to compare the tag to the tag in all 4 lines and figure out whether or not I get a hit. And whether, if I do get a hit, I have to check and make sure whether the valid bit is set. Okay? Is everyone with me so far? Now, on to the physical side of the system. Okay? So we have the physical page offset, that's 6 bits, just like it is with the virtual page offset. We have a 12-bit physical address, so the physical page number is going to also be 6 bits long. This 12-bit address is broken up into 3 fields. 2 bits for the cache offset, because I'm going to assume 4-byte block size. Okay? And I'm going to say there's 16 lines in here, and it's direct map. So the cache index is going to be 4 bits to access one of these 16 lines. And the remaining part of this address, 6 bits here, is going to be the tag that I'm going to use to compare it. So this B0, B1, B2, B3 are the 3 bytes in my 4-byte block that I have for each cache line. Okay? So one thing I just want to point out, which will become, you'll see is important later on in the lecture, the division here between the cache index and the cache offset and the cache tag was actually not coincidentally constructed to break right at this point between the physical page offset and the physical page number. And you'll see why that is later on in the lecture. Okay, so just keep that in the back of your head. So let's look at an example. I guess I'll do this here. Okay, so we've got this virtual address, which is 14 bits, 03D4. 4 times 3 times 4 is 12. Okay, 03D4. Hopefully I did that right. 4, 8, 12. Okay. 03D4. So the CPU presents this virtual address to the memory management unit. What does the memory management unit do with that address? What's the first step? I gave this lecture early in the morning and I just went through this, and then when I went to the second example and actually asked for answers, people were dumbfounded. So I'm not providing any answers. Yes? How does it look in the TLB? So yes, the memory management unit is going to do something to this address and use part of it to look up the things in the TLB. So what is it going to do to that address? Okay, so it's going to divide this into 2 pieces, the virtual page offset and the virtual page number. So if you'll remember, I said that we have a 14-bit virtual address, and it's divided into 2 pieces, 6 bits of virtual page offset and 8 bits of virtual page number, because my page size is 64 bits, which is 6 bits. So my virtual page offset is 6 bits, and my virtual page number is 8 bits. So what is it going to present to the TLB? What's the actual value it's going to present to the TLB?
The first 8 bits. So
The first meaning the left-hand 8 bits or the right? Okay. So we're going to divide this over here. Okay, so the virtual page number is F0F. The page offset into that page is 1, 4. Okay, so it's going to present here 0xF to the TLB. And what happens when it does that? Here we go. So we have to, in the TLB, divide the virtual page number into the TLB index and the TLB tag. The TLB index is 2 bits, and the TLB tag is 6 bits. So this is the TLB index, and this is the TLB tag. So what happens? What does the TLB return? Someone who hasn't answered yet. Yes?
0D.
Okay, why?
This is in the third set with
Oh, it's not in the third set. Let's remember that we are C gods here in this class, and we don't start counting from 1.
yeah, this is the second set.
Oh, actually, wait.
Yeah, it's 1.
Yep, third set. You are right. I am wrong. Third set. I am not a C god. I apologize. So we look at this and we have to compare all these tags, okay? And the TLB tag is 3. And here we are, tag 3, physical page number 0D. So it returns this physical page number 0D. What's next for the TLB? I mean, for the memory management unit? The man in the green shirt. That's you. What happens next? Okay, well, if you don't know, you should have raised your hand before. You got to be following along with this. First of all, you might not care about virtual memory, but if you care about your grade, you're going to have to go through this with a multi-level page table. I guarantee it. So let's get this right. So the TLB just returned 0D, which is a physical page number. How does the memory management unit construct the physical address? Yep, the offset is down here. That gets unchanged. 010100. How do we make this top part of the offset? We've got 6 bits to worry about. Where does that come from? Exactly. That's 0D. I hope I'm doing that right. Okay. So now we have a physical address. What is that address? It's actually, if I wanted to write it down, it's 3, 5, 4. Okay. Now, what are we going to do with that physical address in this system? We're going to look in the cache. Luckily, I have a cache here too. Okay. So the cache has a block size. What did I call that? I forget my terminology now. COCI and CT. Cache offset of 2 bits, because there's 4 bytes in each block, and it has a cache index of 4 bits because I have 16 lines, and a cache tag of 6 bits because that's the rest of the address. So, somebody else want to tell me what happens here?
What's the physical?
Yeah, 354. But we have to divide this piece up into these other fields to figure out what happens next. Someone who has not answered yet. This young lady here. So how do we figure out whether this is in our cache or not? Yep, okay, so we're going to grab these bits here. That is going to be 5. So we're going to go to index 5. And now I've got to figure out whether this is actually what's in here is the correct thing. So how do I do that?
The tag.
Right, so what is our tag here? Luckily, it's 0D. So we indeed get a cache hit. Now, which byte do I actually return? So how did you get that? The cache offset is the bottom 2 bits. So we're going to go to byte 0 in the block, which is a 36. Okay? So this is like the best of all possible worlds. This is what architects dream about, right? Because we got a TLB hit and we got a cache hit. This is the absolute simplest case. Any questions at this point? Yes?
When you said the CT and the PPN are the same size,
I'm going to talk about that later.
okay.
Okay. Let's look at another example. Let's look at address. Don't remember what address it is. Okay, so by the way, I'm going to post these notes that I'm working from online too. Okay, so this is what we just did, 3D4. Okay, so 1CF. So 1CF would be 0, 1. Wait, no, that's not right. 0, 1CF. 0. Hopefully that's right. Zeros with a 1, 2 ones. Yeah. Okay. So, first step. This address gets presented to the memory management unit. What does it do? Somebody who has not answered yet. Man in the aqua shirt.
It splits it the first two, and then the next 4.
Right. Okay, and so what does it do with that once it splits it up?
It sends the first 8 bits to TLB.
Good. So let's see if it's in the darn TLB. Whoops. So how do I figure out if it's in the TLB? Oh, I left this on the board so it's easy to see. We look at the TLB index. In this case, it's a 3. And then we compare the tag, which is 1. So we look for the tag of 1, and we don't. Why do I feel like that's not right? No, okay, it is right. No, it's not right. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I've got a bug here. No, the index is 3 and the tag is 1. That's right. Okay, so it's just I'm hesitant to take a TLB miss because it's so much extra work. Okay, so the tag here, I don't have the proper tag, and that means I get a TLB miss. The TLB doesn't return anything. What happens next? You already answered. Yes, sir.
You go to the address of the page table and you use the page number as the offset.
Awesome. So I haven't specified on here how I find the base of the page table, which was sort of a bug. Remember that we use the page table base register or something like that for the process. But let's assume there's some magic here. Whoops. And here's my page table. So what is the page table going to tell me, sir?
We're 7, so there's no virtual address there.
Dumber, bummer, bummer, bummer. Okay, so here I look in this, I have here my virtual page number is 7. I look inside for 7 and it says that it's not valid. So what does the system do? I'll take anybody's answer on this one. I have an invalid page table entry, yes.
Throw a page fault.
Yep, so now I get a page fault. I haven't specified how I'm going to go get the stuff from disk or whether or not this is just a bad protection error or whatever. So we're just going to leave that here. Okay? I get a page fault. It goes to the kernel. In this case, because I haven't said anything otherwise, I'm going to get a seg fault. This is exactly what happens when you get a seg fault. Okay. So much for that example. That was sort of easy, actually. Okay, one last example. Whoops, wrong thing. Yep, got a page fault there. Okay, virtual address 20. One. Okay, so CPU presents virtual address 20, it goes to the memory management unit. I know you guys are all bored, but just humor me. What happens? Yes, sir.
It splits it, sends the 8 bits to the TLB.
Okay, so we look in the TLB. Whoops, wrong way. Okay, and how do I figure out whether or not things are working in the TLB or for me or not? Before you look there, please divide up the address for me.
You split it, most 6 most significant bits, and then
Good, so I have here an index and a tag. They happen to both be 0 in this case. So that's going to take me to set 0. And I'm going to look for tag 0. I have here, I actually have tag 0, but the valid bit is 0. Is that a TLB hit or a miss, sir?
yes.
Right. So I presented here 0, the virtual page number, and it said you got a miss. Okay, so we don't care about the TLB anymore, sadly. So what happens? Somebody else. We've been through this before. Yes, sir.
Why is it a TLB miss? Why is it not just a seg fault?
So, good question. When I have something marked invalid in the TLB, it just means I don't know. It's just like a cache, a level 1 cache. If it's invalid, you say, what do? You go to main memory to get the result. So that's exactly what's happening here. So for instance, this TLB could have been held data for a different process, let's say. Right? And then I switch processes, so I just mark all the valid bits invalid, and then I leave the tags. Okay. But since you were so kind as to ask me a question, which I sincerely appreciate, what do I do next?
You're going to go to your page table and check your virtual page number.
Good. So there's the page table. What happens?
So your virtual page number is still 0. So you're going to go to the first entry. Valid tag is on, so you're fine. You got 28.
Good. So I'm going to present to the system the virtual page number of 0. The system is going to return to me the page table entry. And now the MMU is going to construct a new physical address. Someone else want to tell me how to construct that physical address? Yes?
You'll use the same VPN,
I'm going to use what?
the same page number. Oh wait, no, sorry, same offset.
Good. So the offset gets copied directly. Remember that. Nothing happens to the offset. It's quite beautiful. Okay, and where do I get the physical page number?
You'll get that from adding the virtual page number to the.
Yeah, so we did that already.
Oh, sorry. So you'll do 28, won't you?
Exactly. Right? So we got back a 28. What the hey? Oh, 28. Okay, good. 12 bits. Okay? So now I'm going to present the physical address of what is that? C20. Did I get that right? No, I didn't. No, because I'm being a moron here. A20. Okay? So what happens next in this memory system? Yes?
Splits it up into different parts of the cache.
Good. How do I do that?
I don't remember the exact number.
They're over there on the board.
Okay, so the first 4 bits will be the index. No, the first 2 bits, sorry, will be the offset.
Right?
Then the next 4 will be the index, and the last 6 will be the cache.
Okay, so I put a box around the index because that's the thing we have to use first. And here's my cache. It's direct maps. That index takes me directly to line 8. I compare the tag, and I see a tag of 24. How annoying. That's the way the processor feels every time it gets a cache miss. It's like, how annoying. Okay, so in this case, let's be a little bit more specific. So I presented this cache, I looked at the index failed to be updated, and so I go to main memory, and now what happens? I don't know what the value is. No, I have no idea what main memory is. So I'm going to return some value question mark at address 0xA20, and what happens to the cache? Yes, sir.
We'll evict the 24.
Good. So the cache is going to then be updated. We're going to put a tag of 28 in here. We'll mark it valid. And then we'll put whatever the data is for these 4 bytes in there. I don't know what they are. And then byte 0 will be returned to the CPU. Incidentally, along the way, I forgot to do something. I forgot to update the TLB. Right, I forgot what the TLB was, index 0, tag 0, so I would actually update this field to have the right physical page number, which in this case was 28. Yes?
Does that happen after it looks it up in the page table, or is it as soon as you?
As soon as the page table entry is returned, if it's valid, it goes into the TLB. I know it's sort of nitty-gritty detail, but actually if you get this, if you can do these examples, you get everything about caching, set associative caching, direct map caching, virtual memory, TLBs. I mean, there's a lot of concepts wrapped up in here. So I highly recommend that sometime in the near future, certainly before Carnival when you're all forgetting everything, you go through these examples and actually go through the steps and convince yourself that you know what's going on. I will post these notes. Do not look at them. Okay? Try and do the example on your own. It's a lot of concepts wrapped up together here. Okay. Any questions before I go on? Yes?
So when the TLB is returning, like it will either return a value or say
Yeah.
like, I missed. How does
Correct.
it do that? Like, how does it
Too
say I
that
missed?
low level detail, not important. Yes.
Is that final return from main memory straight to the CPU or through the cache?
No, it's through the cache. I have this one line here, but it's obviously more detailed than that. Right? Because for instance, we're going to get out of memory how many bytes when we make this access to A20? How many?
The block size.
Yeah, what's the block size? Right, so we're going to get 4 bytes. It happened that I wasn't even thinking at the time, but luckily this example is set up right, that the offset was 0. So it's true I presented A20 to the main memory. If I had been cleverer and made a nicer example, I would have made my offset A21. But then the address the cache presents to main memory is still A20. Right? Because you get the whole block at a time. But then the first byte, meaning byte number 2, if you're a normal human being, from that block would get returned to the CPU. Okay? This is really, really important. Are there any other questions? I'm happy to take questions at this point. If you've got this, you really have everything here. Or almost everything. Okay. That was screen. No. I don't now know how to turn off these lights at the front. Oh, there we go. Okay. Okay, so much for my little examples. Now, I showed you all those examples, nitty-gritty detail, because now I'm going to show you the I-Core 7. Simple, right? Okay, so this is a real system. So what do we see here? Well, first of all, we see like registers, that's for data, instruction fetch. The I-Core 7 has a split level 1 cache for data and instructions. Then it has a unified level 2 cache for both data and instructions. For this core, this little piece here, this big piece here is replicated 4 times. All 4 cores then share the L3 cache. Okay? So we've seen this caching stuff before, but then there's also the TLBs, the memory management unit. There's also a split TLB, one for data and one for instructions. You'll notice that there's different number of entries here. And then there's the L2 unified TLB, even more entries. Then finally that comes down to the memory controller, which, if you're interested in that, take graduate computer architecture. Eventually it gets down to main memory. Okay, so a couple of questions here. Why do you think the designers of the i7 chose to split their level 1 cache into a data cache and an instruction cache? Yes?
You don't have some really commonly used values for each of them corresponding.
Commonly used values, that's exactly why caching works in some sense. But why split them? Yes, sir?
There's only a risk that you're going to get a conflict miss unit if you merge them together.
Okay. So we're going to reduce conflict misses possibly between data and instructions, because really they're very sort of separate. In fact, they have very, very different characteristics. Okay, so tell me if you think I would be a fool. They didn't do this, but if I would be a fool to make the block size for the L1 I cache 10 times bigger than the block size for the D cache. What is it about instruction streams or data streams that might make me want to do that? Yes?
Most likely it would go through in order.
Yeah, so what does that mean in terms of locality?
There's spatial locality.
Yeah, so the instruction stream is very sequential, right? The chances that, what a branch is every 5 instructions, and lots of on average, and lots of branches are just to the nearby neighbor. So the spatial locality of the instruction stream is very high, which means the cost of bringing in a big block is going to be amortized by the fact that you're going to probably hit in it a lot. Okay? If I make my block size really big for my data cache, I'm likely not to use a lot of the data that I bring in. Poor design choice. Okay, so there are differences between the instruction stream and the data stream that make you want to design them a little bit differently. What's another difference between the data stream and the instruction stream that might make you want to design the caches differently? Probably the biggest difference between the instruction stream and the data stream, besides the spatial locality part. Yes?
You're not writing to the instructions.
In general, most non-evil programmers do not write to the instruction stream. The instruction stream is read-only, like the text segment of your program is generally read-only. Because it's read-only, you don't need to worry about things like write back and write through. Your eviction policy is not going to take into account of whether something's dirty, because it's never dirty. So you can make a simpler cache. And in fact, the number of transistors needed per cell is much, much smaller. So the I cache is much smaller than the D cache on the die. Okay, so it's highly beneficial to split these across. It makes it quite annoying for programmers like me back in the day when I would write optimizing programs that would modify their own code to run faster. Because you're not allowed to write into the instruction cache. Whenever you do a write to an address, it goes through the D cache. Sort of annoying. But that's neither here nor there. Generally, the standard is you're evil if you write into the instruction stream. In any case. Okay, so that's why I split that off. It's also why the D cache and the data TLB and the instruction TLB are separated, because there's different characteristics to how you access these things. Okay, so now, remember I talked briefly at the end of last lecture about where you could put the cache. You could either put the cache close between the processor and the memory management unit. That would be a virtually addressed cache. Or you could put the cache on the other side of the memory management unit. It would be a physically addressed cache. And I just said why one is better than the other. Can you tell me, based on this diagram, whether or not Intel chose to make their cache a physically addressed cache or a virtually addressed cache? Okay, we have one virtual and we have one physical. How many say virtual? How many say physical? Okay, so since physical seems to be winning, tell me why you think this is a physically addressed cache.
The unified cache is connected to memory.
Yes, big hint. You'll notice that the cache, the level 3 cache, remember each of the cores goes through here and then it gets to the level 3 cache eventually, is connected to the memory system. What the memory system is, that's way past translation of virtual addresses to physical addresses. So these have got to be physical addresses that are being sent over from the cache, which means the cache is holding physical addresses. Okay, so it's a physically addressed cache. Okay, why is it that we want a physically addressed cache? Why is that a good thing? Yes, sir.
The point of the cache is to make things faster. So if you have a virtual address, you're going to have to go through the whole thing that we went over there and then pass it through the MMU, which is kind of pointless.
So actually, by that argument, you would want to have, if all you care about is making things fast, making one process fast, you'd want a virtually addressed cache. Why is that? Because the processor would send its virtual address directly to the cache. No memory management unit gets involved now. If I have a cache hit, it can return the data right away. Right? So a virtually addressed cache takes virtual addresses and sees whether or not they're in the cache. I never have to translate the address if I get a cache hit. Okay? If I get a cache miss, then I go through the TLB, blah, blah, blah. Okay? So actually, for speed, pure speed, on one process, a virtually addressed cache is going to be faster. And yet, Intel chose to make their cache physically addressed. Yeah?
Multiple virtual processes will share the
Good. So here I just show you the architecture. I don't show you how many processes are running. Remember at the beginning of the lecture, let's see if I can get here quickly. Probably not. Where is this? Fork. Yes, here we go. Remember that here I have this in physical memory. I've got one copy of this virtual address here, virtual address here. Two different virtual addresses from two different processes accessing the same memory. If I had a virtually addressed cache, first of all, I'd have to keep the process identifier in there with the tag to make sure that the right process is allowed to access it. And then I would have to have two copies of this data in the cache, wasting cache space. Okay? But the nice thing about having a physically addressed cache is the cache doesn't have to worry about protection at all. Sorry for the flipping here. It doesn't have to worry about protection because the memory management unit already dealt with it for me. Once I get an address here, it's a physical address, already safe. I know it's in memory. I know you have the permissions to access it already. Somebody else's responsibility. I don't need any process identifiers in here or anything. So a physically addressed cache might be a little slower, but it's a whole lot safer. Okay? And it's much easier to use when I'm running multiple processes at the same time. Okay, so let's look a little bit more in detail at i7. Same basic symbols that we've been using all along. Okay, it's complicated. It's a real processor. Here's my CPU. It presents a virtual address, which remember is broken up into two pieces, a virtual page number and a virtual page offset. Now you'll notice that this totals only 48 bits. I want you to pretend that that's not true. I'm not going to tell you even more gory details about this system. Okay? So yes, it's a 64-bit address machine. Yes, you manipulate 64 bits of addresses. They all matter, but some of these address bits are hidden, even from this diagram. Okay? So let's just pretend that that doesn't exist. Okay, so we have this VPN, and our TLB now has 36 bits. 4 bits for address, 32 bits for tag, because I told you that there were 16 sets and it was 4-way associative. Okay, just like our example, in fact. Well, our example had only 4 sets, but whatever. 4-way associative. If you get a TLB hit, then you come down here, you found this index, it matched on the tag, the page number comes directly out of the TLB, and now I've constructed my physical address, which is 52 bits. Okay? Because of this 12-bit here, you know that the pages are 4K in size. Now, let's say I get a TLB miss. Oh, man, what a bummer. Okay? If I get a TLB miss, now what happens is I take my virtual page number and I break it into 4 fields of 9 bits each. So I have a 4-level page table hierarchy. Okay? Levels 1 through 3 give me pointers to other page table bases, and level 4 actually finds me the page table entry that returns a physical page number. Yes?
Is 4 generally a good level for a page table hierarchy, or what's like the optimal level?
I have no idea. 4 is what they chose, but there's a reason why they chose it. They did a lot of simulations. But one thing I want you to think about, there's 36 bits in this virtual page number, and each one of these is 9 bits long. Why do you think that they chose 36 bits and made it a 4-level hierarchy, at least based on these numbers like 9? What's sort of magic about that? Let's think about physical addresses. The physical addresses are 52 bits in length. Okay? There's also some permission bits and stuff like that. So what's a good size? What do you think is a good size for a page table entry on this system? How many bytes do you need? I know I need at least 52 bits, which 52 divided by 8 is 7 if you're a computer scientist. Okay? 7's like a bad number though, right? I'm a computer scientist after all. The only thing I know how to do is take powers of 2. So let's say I make these 8 bytes long. So 52 divided by 8 bits is actually 8. Close enough anyway. Okay? That gives me room for permission bits and stuff like that. So my page table entries are 8 bytes each. Given that they're 8 bytes each, what's sort of magic about this 9 number? I have 9 bits in each one of these fields. Yep.
Valid bit.
Oh, that's in here in the 8 bytes, right? So this is 9 bits, and I'm telling you that the entry, each entry of those addressed by those 9 bits is 8 bytes long. How big is one of these page tables? One of these blocks. How many bytes is one of these blocks here? This should be a simple math question. Yes?
4 kilobytes?
Yeah, 4K. Why? There's 2 to the 9 entries. Each entry is 2 to the 3 bytes. 2 to the 9 plus 3 is 2 to the 12, which is 4096. What's the size of my page? Also 4096. Hey, magic. Okay? So remember that page tables and page table entries are just data sitting in the memory system. I make each one of these a unit of a page, and then if I fault, remember that every time I make an access to memory, I present a page table entry address to the memory system, it's going to go, and if I fault, it's just going to page it in like any other data. And I get in exactly one page, I restart the kernel, and it goes back, and now it can go to the next level. Okay? So I don't know if 4 is the right number optimally, but it certainly works out nicely here. Okay? Okay, so I've gotten my physical page number back by making these 4 memory accesses. Okay? Now I have a physical address. The physical address goes to my cache. I break that up. I said that my cache block size was 2 to the 6, 64 bytes. I have 64 sets, so I have 6 bits there, and I have a 40-bit tag. And then I do that if I get an L1 hit, then it comes back to the CPU. If I get an L1 miss, then I've got to present the whole memory to the level 2 cache, and then the level 3 cache, and memory, etc. Whoa. So you can see I've simplified this diagram tremendously because I don't even have separate stuff there. And I also didn't tell you what's happening with the high order bits here in the 64-bit address space. And there's no permissions checking, whatever. You get the idea. Okay? So let's actually look at what those page table entries are like. So in the level 1 through 3 page table entries, what we have is a whole bunch of permission bits. I'm not going to go over these right now. And then the page table base address for the next level in the hierarchy. Okay? If that page table is loaded in memory, in that case the p equals 1, the child page table is present, this is like the valid bit that I've been talking about all lecture. If this valid bit is 0, then there's information in this to store where on the disk that actual page table is located. The level 4 page table entries have the physical page number, the valid bit. If it's not valid, it tells us where we can find that on the page. And then a whole bunch of permission bits. Right? Do I have permission to read and write this particular thing? Is it user mode or kernel mode? Is this particular page going to be treated as a write-through page or a write-back page? You might remember from last lecture I made the very strong case that your virtual memory system wants to be treated as a cache that is a write-back cache, because otherwise every time you write to a page it would have to write it back to disk. Okay? But there are cases where you don't want it to be write-back. Can anyone think of a simple case where this is true? Okay, I'll leave it as a thought experiment. I don't want to take the time to think about it right now. You can also say, I don't want you to use the caches. I want you to go directly to main memory. A similar case is this in some sense. There's a bit here set by the MMU. If you ever access this particular page table entry, which the MMU uses to implement its least recently used policy. So you know you actually touched this. Then there's a dirty bit. Once you load the page from disk, it's clean. But if I write to that page and I'm using the write back policy, I have to know whether I've written to that page at some point, because then when I evict it, I've got to write it back to disk. Okay? So I have a dirty bit that tells me whether or not there's been a write to this. And then some pages are so important that I want to keep them on the TLB even if I make a switch from one process to another. Okay? What page might that be? What? It could be shared files, but more it's like the kernel, right? You're switching from one process to another, so when you do that, you don't want to throw out the kernel's page table entries. That will really slow things down, right? So you keep those in the page table. You keep those in the TLB. Okay. So this is actually how it works. I'm breaking this up into these 4 levels. If I get a TLB miss, I'm going to use this, what I have previously been calling the page table base register, but the I7 people call it the CR3, which tells me what the base of this particular level 1 page table is. Then I use each piece to index, and I keep doing that all the way through, and then I get a physical address. Each entry in this first table is good for 512 gigabytes of memory. Right? Because you can think about it, there's 2 to the 9, 512 entries in each one of these. So it's 512, one of these is 512 times 512 times 512 times 4K. That's how much memory it covers. Okay, so this multi-level hierarchy allows me to save a tremendous amount of physical memory that would otherwise be wasted if I had a single level page table. Right? We talked about it. It would take 32,000 terabytes of data. 2 to the 64 is a really big number. Questions? Okay, so now remember, back when I talked about the example, I said it's no coincidence that I broke the physical address up into 3 components for the cache, the offset, the index, and the tag, such that the index and the offset were in the physical page offset part of the address, and the tag was as big as the physical page number. And Intel does the same thing. They're not stupid. So here's the idea. I have my virtual address. That's what the CPU presents to both the memory management unit. We have to turn that virtual address into a physical address. That takes time. Even if I go through the TLB, it takes time. It would be sort of nice if, in parallel to translating the virtual page number to the physical page number, I could start figuring out whether or not this address is going to be in the cache. And by breaking up the cache parameters such that the index and the offset are all in the virtual page offset, that doesn't change during translation. I can immediately use the cache index part of this virtual page offset to find the set in the L1 cache. Okay? Very cute trick. This is called a virtually indexed, physically tagged cache, right? Because the index comes from the virtual address. It happens to be the same as the physical address, this part of it. And then when I get back the physical page number, that's the cache tag, and I go and see whether or not it satisfies this, and if I got a hit, I can return it immediately. And if you're an electrical and computer engineer, you know that I can do things like pre-charge these lines and get things set up, so it's actually much, much faster. Okay, this is a beautiful idea. So if you have a cache hit, it's going to be quite fast. And that's what computer architects try to do. They try and make the common case fast. The unusual case can take forever. It never happens. Software architects too, for that matter. Okay? So now here I have a question for you. This idea basically only works if when I have a cache hit, I also have a TLB hit. Because if I don't have a TLB hit, I've got to start making different memory references to get my page table entries. What is the likelihood that I have an L1 cache hit and I have a TLB miss? Why is it low? Why are you incredibly more likely to hit in the TLB if you were also going to hit in the L1 cache? Yeah, because remember that the cache line is only 8 bytes long, but the TLB entry is good for 4K. So the chances that you would have it in your cache and not have it in your TLB would be pretty weird. Okay? Which is exactly what you want here, because when you hit in the cache, you want to make sure that this whole thing is very fast. Okay? You might very well have a TLB hit and a cache miss. Okay? Then this didn't save me anything, but I want to make the common case fast. And a cache hit is the common case, luckily for us. Okay, it is now, what time is it?
46.
Okay, there's no way I can do this in 4 minutes, and I'll just confuse you. Yeah, okay, so I'm not going to confuse you. Okay, so here's the deal. The TAs will cover some of this, and I will tell Greg, who will be back on Tuesday, I'm sure much to your delight, that he should maybe go over this quickly. Okay, any questions since we have a few minutes? No? Enjoy your evening.